In the vast library of doomsday scenarios, few stir a deeper, more primitive fear than the image of a rock from space hurtling toward Earth. A celestial bullet, forged in silence, older than time itself, moving at tens of kilometers per second with no emotion, no purpose, just the pure, blind momentum of the cosmos. An asteroid impact is not just a catastrophe. It is the final catastrophe, the kind that doesn't leave anything behind to record it. 66 million years ago, one such impact marked the end of an era. The age of the dinosaur creatures that had ruled the Earth for over 150 million years was erased in what may have been just a few hours. But they weren't the only ones. That impact darkened the skies, poisoned the air, collapsed ecosystems, and ended 75% of all life on the planet. Not with fire alone, but with what came after. The ash that choked the sky, the cold that killed the crops, the silence that followed the roars. This is not myth. It's not exaggeration. It's etched in the rock record of our world. And it is only one example of many. Unlike other apocalyptic fears, nuclear war, climate collapse, pandemics, an asteroid gives no negotiation, no politics, no delay. The moment we know it is coming may also be the moment it is already too late. No leader can reason with it. No border can stop it. No shelter can outlast it. But what exactly is an asteroid? What makes it different from the shooting stars we wish on, or the meteorites we see in museums? It begins with definitions cold, scientific, and yet utterly vital. A meteoroid is a small chunk of rock or metal drifting through space. Most are the size of pebbles or dust, and when they enter Earth's atmosphere and burn up, they become meteors, brief flashes across the sky. If they survive the descent and strike the ground, they become meteorites. But asteroids are something else entirely. They are vast, solid bodies, some hundreds of meters wide, others stretching into kilometers. They orbit the Sun, mostly between Mars and Jupiter in the asteroid belt, but some drift dangerously close to Earth's path. When an asteroid enters our atmosphere and strikes the surface, we call it an impactor. It's this class of visitor fast, massive, and rare that holds the power to end civilizations. Now imagine this. One such object, just 10 kilometers across, begins its descent. That's all it takes. Just 10. Not the size of a planet or even a city. Something smaller than the island of Manhattan. But moving at 20 kilometers per second, it carries more energy than all the nuclear weapons on Earth combined. And the most terrifying truth? Earth has no natural defense. There are no shields, no force fields, no planetary instincts to protect us. Our atmosphere can burn up the small ones, sure, but not the giants, not the extinction makers. So what would it look like if it happened now? First, you would see nothing. Perhaps a glimmer in the sky, if anyone were watching through the right telescope at the right time. Perhaps a warning if our instruments detected it early enough. But then, just days or hours later, the heat of re-entry, a shockwave faster than sound, a blinding flash brighter than the Sunday, and then impact. But that's for later. Because before we simulate the future, we need to look at the past, at the scars written into Earth's crust, at the impact craters that testify to just how fragile this planet has always been. At the cosmic roulette we've been playing for 4 billion years and somehow, until now, surviving. But maybe not forever. To understand the danger, we must first examine the history. Not human history, but planetary history. The kind written in stone and buried deep beneath oceans and deserts. Earth is scarred with impact sites, some so large they can only be seen from space, and each one tells the story of a moment when everything almost ended. The most ancient and perhaps most terrifying of these scars is the Vredefort crater in South Africa. It stretches over 300 kilometers across, making it the largest confirmed impact structure on Earth. Scientists estimate that the asteroid that struck here had a diameter between 10 and 15 kilometers. That is all it took to shake a planet. The impact happened roughly 2 billion years ago, long before complex life emerged. But if such a strike occurred today, civilization would not survive it. Not because of the explosion alone, but because of what comes after. Then there is Chicxulub, a name that echoes through extinction. Located on the Yucatan Peninsula in Mexico, this crater is about 180 kilometers wide. It marks the spot where, 66 million years ago, A space rock delivered one of the most decisive endings in Earth's biological history. That asteroid, roughly 11 kilometers in diameter, ended the reign of the dinosaurs, triggered global wildfires, launched debris into orbit, and blocked sunlight for years. Photosynthesis halted. Food chains collapsed. The age of giants died not in fire, but in famine and cold. The third great wound lies in Canada, in a place called Sudbury Basin. It is one of the oldest and most eroded impact sites on the planet.
Meteoroids
Some
are
researchers
small
believe
pieces
it
of
was
rock
not
and
even
debris
formed
in
by an
space.
asteroid,
When a
but by a
meteoroid
comet
enters
fragment,
Earth's atmosphere,
a ball
it
of
becomes
ice
a
and
meteor.
rock that slammed into Earth 1.8 billion years ago. The crater now measures about 60 kilometers in diameter. Over time, erosion has hidden much of its original shape, but the violence of that moment still lingers in the rocks beneath. These three events represent only a handful of the large-scale impacts we know about. There are many more, smaller but still devastating, and they all lead us to a chilling conclusion.
This visualization
Impacts like these are
compares
not
a small
hypothetical.
meteoroid to a
They have
massive
already
asteroid.
happened, and they will
Between
happen
Mars
again.
and Jupiter lies the
The
solar
frightening
system's
part is how
asteroid
little
belt,
it takes.
a chaotic
An
swarm
asteroid
of
only
countless
1
minor
kilometer
planets
wide
and space rocks.
is enough to cause global catastrophe. It can ignite the atmosphere, create a shock wave that flattens forests and cities, and inject dust and sulfur into the stratosphere, dimming the sun for months. With temperatures dropping, crops would fail. Societies would unravel. Millions, even billions, could starve. And these events are not ancient relics. They are reminders that Earth is vulnerable. In fact, the only reason we are alive today is timing. The impacts we study happened before us, not during us. So what makes asteroids so deadly? The answer lies in speed and energy. A typical asteroid enters Earth's atmosphere at a velocity of around 20 kilometers per second. That is over 72,000 kilometers per hour. The kinetic energy released on impact is measured in megatons, often exceeding the total yield of all nuclear weapons ever detonated. Now, imagine that kind of force striking near a major city. Not in the ocean, not in the desert, but somewhere with skyscrapers and highways and airports. The result would not just be local devastation. It would trigger chain reactions: financial collapse, mass migration, panic, chaos. Civilization as we know it would not recover quickly, if at all. This is why scientists study craters. Not just to learn about the past, but to prepare for the future.
Unidentified object
Every
detected.
scar on Earth is a
Impact
warning.
trajectory confirmed.
And if
Seek
history has
shelter
taught us
immediately.
anything, it is that these cosmic killers do not announce themselves. They arrive in silence, riding shadows, and change the world in seconds. And the truth is, some of them are already on their way. Imagine this. Somewhere in the cold darkness beyond Mars, a rock the size of a mountain begins to drift slightly off course. Perhaps it was nudged by the gravitational pull of Jupiter, or by the subtle push of sunlight over millions of years. Perhaps it was broken from a larger body, or has been wandering alone since before Earth was even formed. Regardless of its origin, its path has changed, and it is now headed straight for us. The warning may come weeks before impact. If it is small, maybe only days. In the control rooms of NASA, the European Space Agency, and observatories around the world, alarms would flash. Telescopes would focus. Supercomputers would run simulations night and day. The question would not be if it hits, but where. As it nears Earth, the asteroid will be traveling at around 20 kilometers per second. That is over 70 times the speed of sound. In space, it is silent. But when it meets the atmosphere, it will scream. Friction will ignite its surface. The air in front of it will compress and superheat, forming a glowing shock wave hotter than the surface of the Sunday. The moment of impact will be almost anticlimactic. A white flash, a tremor, a roar that comes seconds later. Then nothing. But that moment will be only the beginning. If the asteroid is 10 kilometers across, the explosion would release energy equivalent to several billion tons of TNT. At ground zero, everything within a radius of 1,000 kilometers would be vaporized or flattened instantly. Entire cities would disappear. Mountains would crumble. The shock wave would travel around the globe, circling the Earth several times before dissipating. If it strikes the ocean, the result is no less terrifying. A wall of water dozens of kilometers high would rise, forming mega tsunamis that would race across the seas at jet speeds. Coastal regions on every continent would be swallowed.
Civilization
Ships would
not
vanish.
survive.
Ports would be erased. Then comes the sky. Dust and debris launched into the atmosphere would form a thick, dark veil around the planet. Sunlight would dim. Temperatures would plummet. This is what scientists call impact winter. Within weeks, global agriculture would begin to fail. Crops would wither. Livestock would die. Supply chains would break. The modern food system, already stretched thin, would collapse entirely. In the cities, chaos. Fuel shortages. Riots. Looting. Hospitals overwhelmed. Communications failing. And worst of all, hunger. Those who survived the blast would face something far crueler. A world without light, without warmth, without order. A world slowly dying not from the impact, but from the silence that follows. In this model, the final death toll is not measured by craters or collapsed buildings, but by the seasons that never return. Without sunlight, photosynthesis stops. Without crops, famine begins. And with famine comes war. This is not speculation. These events have happened before. And our simulations, using current global infrastructure, show that even with preparation, humanity would not be ready. Not for something of this scale. Not yet. Even a smaller asteroid, only 1 kilometer across, would still be enough to destabilize entire continents. It would not wipe out humanity entirely, but it would end the modern world. And the scariest part? We have no idea how many of these objects are out there, still unseen. We do not know which one will be next, or when. We only know that one day, the countdown will begin. The threat is real. But how close are we to facing it? In April of the year 2029, a massive asteroid named Apophis will pass dangerously close to Earth. How close? Within 30,000 kilometers. That is 10 times closer than the Moon. Closer than some of our satellites. In space terms, that is a bullet grazing your skin. Apophis measures approximately 340 meters across. That is about the height of the Eiffel Tower. If it were to strike, it would release energy equivalent to more than 1,500 nuclear bombs. Entire metropolitan regions could be erased. But scientists say it will miss us barely. Still, the mere fact that it is coming so close has shaken the scientific community. Because Apophis was discovered only in 2004, for months, calculations showed a small but real chance of impact. And although it was eventually ruled out, the event reminded us how little warning we might have when the next object appears. Then there is Bennu, a carbon-rich asteroid roughly 500 meters wide. Bennu has a small chance of striking Earth in the late 22nd century. But long before that, it could be deflected or studied if we act in time. It has already become the target of missions like OSIRIS-REx, which landed on its surface and collected samples. Bennu is a case study for future threats. We can track it. We can approach it. We might even move it. But many objects are not like Bennu or Apophis. They are smaller, darker, harder to detect. Some come from directions we are not watching. On February 15, 2013, one such asteroid entered Earth's atmosphere over Chelyabinsk, Russia. It was only about 20 meters wide. It exploded in midair with the force of 30 atomic bombs, shattering windows in 6 cities and injuring over 1,000 people. The world had no warning. It arrived out of the morning sun, invisible to telescopes. That same day, by eerie coincidence, another asteroid the size of a football field passed within 28,000 kilometers of Earth.
The depth scans show unprecedented
separate
energy
events,
readings at the core.
Just hours
the
apart.
predictive model suggests
Neither
a
of them were
high-magnitude
detected early
cosmic
enough to
ray burst
respond.
within the next cycle.
These are not isolated incidents. Every few months, an asteroid passes within lunar distance. Most are harmless. Some are not. The problem is that we have only mapped about 40% of the near-Earth objects larger than 140 meters. That means more than half are still unknown. Floating out there in the darkness, on paths we have not calculated. And even those we do track can surprise us. Orbits can shift. Gravitational influences from planets or the sun can bend their paths over decades. A miss today does not guarantee safety tomorrow. This is why international agencies have started compiling watch lists databases of every known asteroid that crosses Earth's orbit. They assign risk levels. They simulate future positions. They predict probabilities. But predictions are not certainty. And time, as always, is the most precious resource. Detecting an asteroid 10 years in advance gives us options. 10 days? Not so much. 10 hours? There is nothing we can do. So is it coming? Maybe not today?
Weeks
maybe
until
not
impact.
next year. But statistically, yes. Eventually, one will come. And if we are not ready, we will have only ourselves to blame. Not every danger roars. Some arrive silently, painted in the black of space, waiting for our blind spot to pass across them one more time too many. For the first time in history, humanity is trying to fight back. Not with missiles, not with prayers, but with precision, patience, and science. In the year 2021, the National Aeronautics and Space Administration launched a mission that sounded like something from a science fiction movie. Its name was DART, the Double Asteroid Redirection Test. Its goal was as bold as it was simple: smash a spacecraft into an asteroid and change its path. The target was Dimorphos, a small moon orbiting a larger asteroid called Didymos. Both are harmless to Earth, floating millions of kilometers away. But they were chosen for an experiment that could save the planet. The DART spacecraft was about the size of a refrigerator. It had no explosives, no warhead, just mass and speed. On September 26, 2022, it struck Dimorphos at over 6 kilometers per second. From Earth, telescopes watched the impact in real time.
Everything within a
The
radius
asteroid's
of
orbit
1,000
changed, not by
kilometers
much,
would be vaporized
only a few minutes
or
shorter, but it
flattened
proved the
instantly.
concept. A human-made object had redirected a celestial body. That success echoed far beyond the asteroid belt. Because if we can change the course of one rock, we can change others. With enough warning and enough power, we can turn killers into bystanders. Other nations are not staying idle either. China, for example, has proposed launching 23 Long March 5 rockets at a large asteroid called Bennu. Their simulations suggest that coordinated impacts could shift its orbit enough to miss Earth entirely, even if it were on a collision course. The strategy is based not on one massive hit, but on multiple precise nudges, like steering a ship by tapping the rudder repeatedly. The logic is clear. The sooner we act, the less force we need. A tiny deflection today can mean millions of kilometers of distance tomorrow. That is the power of orbital mechanics. But timing is everything. To deflect an asteroid, we must first detect it. That means building better telescopes, especially space-based ones that can see the sun-facing side of Earth, the direction many surprise asteroids have come from. It means international cooperation, shared data, shared resources. Because space is not divided by borders, and the next asteroid will not ask for a visa before it strikes. We must also prepare for the worst. Not every asteroid will be suitable for deflection. Some may be too large, too fast, or discovered too late. In those cases, impact is inevitable. Then the focus must shift to emergency response evacuations, disaster relief, food stockpiles, radiation shelters, long-term climate planning. Planetary defense is not just about spacecraft. It is about survival systems.
Nothing left.
It is about knowing where to run, what to protect, who to save. Because when the clock starts ticking, the world will have days, not months. The good news, we have started.
We are not ready for this
DART
scale.
was only the beginning. More missions are planned. More technology is being developed. The science is real. The math works. The challenge is political will, sustained investment, and global awareness. Because Earth has no second chances. There is no backup planet, no cosmic insurance. And the next asteroid will not care about our schedules. It will come when it comes. The only question is whether we will meet it with open eyes and something more powerful than fear. When facing an asteroid the size of a city block, what do you send to stop it? A robot? A mirror? A rocket? Or do you send the most powerful weapon humans have ever created? The idea of using nuclear weapons to stop an asteroid has been around for decades. In theory, it is simple. Detonate a nuclear device near the asteroid's surface. The explosion vaporizes part of the rock, creating a plume of gas and molten debris that pushes the remaining mass in the opposite direction. Done correctly, this blast could alter its orbit just enough to miss Earth. Some simulations show that nuclear devices can be 10 to 100 times more effective than non-nuclear
had no
impactors in
warning.
deflecting an asteroid. A
How
single
could we have missed
warhead,
this?
properly placed, might succeed where dozens of kinetic strikes would fail. When time is short and the object is massive, nuclear force could be the only tool powerful enough to matter. But there are problems. Big ones. First, precision. To be effective, the device must detonate at exactly the right altitude, angle, and timing. Too far, and it does nothing. Too close, and it could shatter the asteroid into 1,000 fragments, all still headed for Earth. Second, unpredictability. Unlike controlled missions like DART, a nuclear detonation creates chaotic results. The shape, density, and spin of the asteroid all affect how it reacts. Some might absorb the blast. Some might crack apart. Some might tumble in unpredictable directions, turning one threat into many. Third, politics. International treaties like the Outer Space Treaty of 1967 and the Partial Test Ban Treaty strongly discourage the placement and use of nuclear weapons in space. Even in a planetary emergency, launching a nuclear warhead into orbit would trigger massive diplomatic alarm. Who gets to decide? Who holds the codes? Who verifies the target? Because when you send a nuclear missile into space, you are not just battling physics, you are battling trust. That is why scientists are increasingly turning to non-nuclear alternatives. These include kinetic impactors, like DART, that push the asteroid off course through momentum. Gravity tractors, spacecraft that fly near the asteroid for months or years, using their small gravitational pull to tug it off its path.
We have a confirmed
Laser
orbital
ablation,
crossing for
firing
designation
concentrated beams of light to
7482.
vaporize
Haroon,
material from the
alert
surface,
the Global Defense Network
creating thrust in
immediately.
the opposite direction. Solar sails, massive reflective surfaces that change the asteroid's velocity over time using sunlight alone. Each method has its strengths. All are safer, more controllable, and easier to test in peace. But they require time. Months, even years of lead time before the impact, which brings the debate full circle. If the warning comes early, we can be precise, measured, and safe. But if the warning comes late, if the asteroid is just months away, then there may be no choice left. The nuclear option would move from the last resort to the only resort. That is why scientists continue to model both paths. Because when the sky darkens and the countdown begins, decisions will come fast. There will be no time for politics, no room for theory, only action. And the weapon we choose may not define just our survival, but the shape of the planet that remains. When the stakes are extinction, even the strangest ideas deserve attention. Some scientists have proposed a method so quiet, so indirect, it almost feels like a trick. Do not explode the asteroid. Do not hit it. Just change its color. This is the albedo effect, and it begins with light. Dark surfaces absorb sunlight. Light surfaces reflect it. On Earth, this is why black asphalt burns your feet in summer, while white sand stays cool. In space, the same principle applies. If one side of an asteroid is painted white and the other black, the sunlight will heat each side differently. Over time, this imbalance creates a small but steady force called the Yarkovsky effect. The asteroid, gently nudged by its own thermal emissions, begins to drift. The drift is tiny, but over years or decades, it adds up. The idea sounds absurd, painting a mountain in space, but it works in the math. The challenge is delivery. How do you spray paint a spinning, tumbling rock millions of kilometers away, traveling at 20 kilometers per second? That is where robotic probes come in. One proposal involves launching small spacecraft that release fine dust or reflective particles onto the asteroid's surface. Others suggest aerosols or foams that harden in place. Some designs even imagine micro-drones, autonomous flying machines that cling to the
We
asteroid
need to build
and coat
better
it in layers of
telescopes,
contrasting
especially
material.
space-based ones.
Another solution is more futuristic. Solar sails. Imagine a spacecraft the size of a skyscraper but paper-thin, unfolding in space like a flower. These sails capture the pressure of sunlight itself, not heat, but momentum, and use it to steer the ship. If such a sail is attached to an asteroid, or even flown close to it, the reflected sunlight can alter the asteroid's path ever so slightly. Others have suggested using giant mirrors. Space-based reflectors could focus beams of sunlight onto one part of the asteroid, heating it unevenly and creating thrust. or lasers, mounted on satellites, could vaporize small amounts of surface material, slowly adjusting its orbit. There is also the idea of a gravity tractor. A spacecraft would fly alongside the asteroid, maintaining a fixed distance. Its own tiny gravity would pull on the asteroid, changing its trajectory over time. No contact, no explosion, just the silent dance of mass and motion. All of these ideas have one thing in common. They rely on subtlety. They do not stop the asteroid all at once. They bend its future, gently and early. But that subtlety requires time, years of preparation, decades of observation. Which means these ideas are not backup plans, they are first-line defenses for the threats we see coming long in advance. Critics call them fantasy. But in a world where the cost of failure is measured in species, even fantasies deserve funding. Because the day may come when we discover a threat too large for rockets, too fragile for nukes, too close for engineering. And when that day arrives, we may need more than muscle. We may need imagination. The sky is not just full of danger. It is also full of possibility. And sometimes, the smartest weapon is not the loudest or the strongest, but the one that quietly changes the ending before the story even begins. There's one more question no one wants to ask. What if we fail? What if the asteroid is too big, or we see it too late? What if every plan breaks down and the sky opens, not in light but in fire? What then? For all our science and strategy, there is still a truth no one can outrun. Earth has no armor. It is a blue marble floating in darkness, exposed from every angle. And some asteroids do not give warnings. They come from the blind side. They are hidden by the sunday. They are silent until they arrive. In the worst-case scenario, where impact is certain and unavoidable, the question shifts from deflection to survival. Who can be saved? And how? Governments around the world have contingency plans. Underground bunkers, hardened shelters, seed vaults buried in permafrost. But none of these are designed for long-term global winter. A planetary impact could drop temperatures below freezing for years. Crops would die. Oceans would acidify. The air itself would carry dust and chemicals that choke both lungs and sky. To survive, humanity would need more than bunkers. It would need a lifeboat, a sealed, self-sustaining habitat, possibly underground, possibly underwater, possibly off-world. This is where the idea of space colonization re-enters the conversation. For decades, it has sounded like a dream, a luxury, a science fiction fantasy, but in the face of extinction, it becomes something else, a backup. Projects like SpaceX's Starship, NASA's Artemis program, and China's plans for lunar infrastructure are more than technological milestones. They may be the early blueprints for a time when Earth is no longer safe. A moon base, a Mars outpost, an orbital station that can survive independently. These are not just scientific goals. They are insurance policies. Because no matter how improbable the next extinction-level asteroid may seem, history tells us it will happen again. It is not a question of if, it is a question of when. And so, we come full circle. From ancient craters in the desert to nuclear deflection missions in the 21st century, humanity has begun to calculate trajectories, to map the darkness. But learning is not enough. Survival takes action. And in the end, it may take a choice we never wanted to make. To leave. Not to escape responsibility, but to preserve memory, knowledge, life, the very idea of us. Because if the sky ever falls and Earth becomes a tomb, something must remain to say that we were here. That we built cities and wrote poems and wondered about stars. That we did not go quietly. Maybe that is why we build rockets. Not for war, not for pride, but for hope. Hope that, somewhere, far from the crater, something human survives. And as we close this journey through apocalypse, that is the message left behind. Earth is fragile. Life is rare. But imagination is infinite. The next impact may come in 20 years, or 200, or tomorrow. But if we prepare, if we imagine, if we choose to act not from fear but from wisdom, then perhaps, when the final asteroid comes, it will not be the end. Only the beginning of the next